Hiya! So in this video, we're going to be talking about the cumulative distribution function. So basically the idea here is we want to see how the distribution accumulates over time. In other words, what we want is, so if I have some distribution, so we'll use the normal bell curve. If I want to figure out things over time, I want to figure out what the distribution is over some interval. So in other words, normally we look at it in a range, but we can look at it just everything below some number. So we can look at the probability of everything being below some number. And this is called the cumulative distribution function. And normally we denote this as capital F of x of x. Whoop, I thought I hit blue. Cumulative distribution function. And that's it. So it seems super complicated, but it's actually not too bad. Like for example, for our normal distribution function, right? For the standard normal distribution, we already saw what this is. This is our phi of x. So when we plug in phi, what we're doing is really saying phi of x is equal to f sub x of x for the for a standard normal distribution. So knowing this, we can actually take this a little further, right? So if I want to figure out the probability from a of a less than or of x less than or of b, oops, that should be a capital X. Well, what is this? So if I have some function and I want to know from a to b, well, I can grab the area of b, and I can remove the area of a, right? This is f of x of b, and this is f of x of a. So if I want to subtract them, what I'm just basically doing is literally just subtracting them. F of x of b minus f of x of a. But notice how, so in other words, oh, sorry, this is what I said for the phis. I wanted to write phi here. So we can do this with anything, right? So what we have is, let me write this above because I want to write this in two different ways. B is equal to f sub x of b minus f sub x of a. Remember that the other way of writing this is the integral from a to b of little f of x, our probability density formula, dx. So notice here, this should remind you of fundamental theorem of calculus. Right? It looks identical. And that's because it is. That's basically where this idea is coming from. Now, notice one little thingy. And I guess... Yeah, so I guess here I actually wrote this wrong. I meant this. So notice here, now there's a slight difference here, right? So here I have less than or equal to, and then here I should have written just strictly less than. And the question becomes, well, what's the difference between this and this? Why is there a difference? And the reason we're allowed to flip-flop between them is because for a continuous distribution, the probability at any point is equal to 0. So adding a in or out is basically the same. So the probability that x is greater than, or sorry, is less than or equal to x, this is equal to the probability that x is strictly less than x, because we can just add nothingness to it. And this is basically how continuous distributions are defined. So basically what we have is a distribution is continuous if its cumulative distribution function is a continuous function. And what can be shown is that if a distribution is continuous, then we have the property that x is equal to 0. Always. So it's not too bad. So what this basically means is changing this to this doesn't change the probability. So this is identical to this, right? So this is equal to 1 minus p of x less than or equal to x. So this is true for everything, for every key point. And then this one, which is equal to 1 minus p of x less than x, right? Notice how we're able to convert f of x to this. This is only true for continuous. Only true for continuous, this one. So notice these are different. Maybe I should draw like a little line between them so they're separated. They're different. So this is something to note and something to kind of remember. So what we're going to do is actually look at the cumulative distribution function in discrete case, continuous case, and kind of see what they look like in both cases. So we'll stop here for this video, and I'll see you in the next video to kind of talk about the discrete case. So I'll see you then.